We've obviously got time for questions. So there'll be 5 minutes for questions. So please feel free to submit your questions on the green button down below your screen. First up, we have Anteris Tech, ASX code AVR. It has a market cap of around $35 million. We have with us today Wayne Patterson, is the CEO of the structural heart company, as I said, anteris Technologies. The company's core technology is ADAPT, the tissue treatment technology on which their structural heart products are built. Initially commercialized to treat heart defects, ADAPT is the only engineered tissue with clinical data to support 10 years of anti-calcification and has already been used in over 20,000 patients. Wayne, you're online. Over to you. Thank you.
Thanks, Tim, and thanks for having me, and good afternoon, everybody who's tuned in. Today, I want to tell you about anteris and what we do. Anteris is in the business of making the world's most durable heart valve. So that's a big claim. I'm going to hopefully tell you why that claim is valid and why it's important. Next slide, please. Thank you. So anteris is a structural heart company. What that means is we make products that are used in treatment of heart disorders, cardiac disorders, and it's solving critical issues there. We're competing in a potential market space that will be worth about $8 billion US by 2025. It's about 4.5 at the moment, growing significantly, about 16% compound annual growth rate. We have two key assets that are unique to anteris and that nobody else has. One is ADAPT, which is a treatment of the material that we build our valves out of. Now, ADAPT is very unique with a lot of data behind it, and I'll talk a little bit about that in a minute. But we have 20,000 patients who have ADAPT products inside of them globally, so it's, of course, not experimental. And our second asset is called DuraVar. You'll note the AVR, it stands for aortic valve replacement. It's also the same as our ticker. Now, the DuraVar valve is built with ADAPT, which is a treated collagen. But it's also novel in its own right. It's a single-piece 3D molded valve, and it's the only valve of that kind in the marketplace. So both the valve has unique properties of its own, and it's made up of material that has unique properties. And I'd like to talk about that. Next slide, please. So what are these valves and how are they used? Transfemoral aortic valve replacement, or TAVR, is the procedure that we are very much focused on. Now, when you have a valve or a condition called aortic stenosis, your native valve calcifies, it has to be replaced, it stops working. There are two ways to do that. If you look at the bottom right, you'll see a graphic there of a patient with their chest open. So previously they would open somebody's chest, put their heart on bypass and replace that valve. It's a very long procedure and the recovery time is significant. Typically also patients at high risk, elderly patients, are not good candidates for this kind of surgery as the mortality rate is very high. Several years ago, there was a technique invented that basically replaced, to some extent, opening up the chest by putting the valve on a catheter, inserting that in the femoral artery, which is down near your groin, driving it up over the aorta and dropping that valve in place at the top of the annulus. And that procedure is called TAVR. We make valves for that procedure. Next slide, please. As I said, the marketplace is growing at about 16% and worth about $8 billion by 2025. And there's a really important reason why it's growing so quickly, which I'd like to show. Next slide, please. So one of the problems right now, of course, is that patients who need a valve replacement due to aortic stenosis get replacement valves. Now, there are a couple of valves in the market. The picture you see here is one of the market-leading valves. That's a replacement valve. What you'll note there is that valve is full of calcium. So these valves that are going in are calcifying again, which means the replacement valve needs to be replaced. What happened recently is that the FDA approved the use of these valves in what's called low-risk patients. Now, low-risk patients are younger patients. Now, that approval was only last year. That means with younger patients getting these valves, the valves have to last longer. They have to be more durable. Not only should they not calcify, but they also should not wear out mechanically. Next slide, please. You can see this graphic here. Typically, patients who are getting a TAVR valve, a procedure, and they're about 85 years old, the so-called high-risk category, up until very recently. So those patients may be at 85. If that valve goes another 5 years, patients generally getting to 90 probably not go much further than 90. They die of other causes. So the valves were doing okay. But as now the FDA has approved it in younger patients, valves will go into patients who can be in their 70s or even 60s. So those valves now have to last 10, 15, or even 20 years, the life of the patient. The current valves in the market do not have the longevity or the data to show that they last that long. Next slide, please. Next. Next slide, please. So ADAPT is the treatment material, the material we use to make our valves. It's been used in about 20,000 patients globally, but uniquely, we're the only company in the world that has shown that our material does not calcify in humans over a 10-year period of time with a very large data set. Nobody else has that data, so it's really important to note the uniqueness of that. Next slide, please. And next. Now, one of the key issues to note is that beyond calcification, there are other things going on with the valves that make them wear out. The picture in the middle you see here is another valve from another company in the space. And again, it's a replacement valve. Again, you'll note the calcium buildup in that valve. So these replacement valves are not lasting. There are 4 key areas that we address that affect calcification in these valves. Number one, on the bottom left, these valves are shipped in a chemical called glutaraldehyde. Glutaraldehyde keeps it sterile, but it's also highly toxic. So when the valve comes out in the OR, the valve is rinsed and most of the GA is rinsed off of that valve. However, it's well known that there is residual GA remains on that valve. Now that residual glutaraldehyde causes inflammatory responses, which leads to calcification. That's point number one. The DuraVar valve has no residual glutaraldehyde. We're the only one that doesn't. Point number two, and probably the most important from where I sit, these valves are made up of collagen that comes from animals, bovine and porcine. And the reason they use the collagen is it has the physical characteristics that is desirable in a valve. However, it comes with downsides. The collagen coming from animals has DNA in there that's foreign to your body. So your body will try and reject that DNA. The current valves have remnant DNA on them when they're placed, and that causes an immunological response, which leads to inflammation and calcification. DuraVar is the only valve that has 0 remnant DNA in the scaffold. So that's quite an important one. If you go to the far right, the other one is the physical design and the mechanics of the valve. All of the valves in the market at the moment are made up of 3 pieces of tissue sewn together. DuraVar is the only valve that's made up of a single piece 3D molded design. It's much more anatomically correct. But what we've found is it has about 35% less wear and tear on the leaflets. Now, this is outside of the calcium part. It just wears out more slowly. And importantly, it has a bigger opening area. So it seems to be hemodynamically superior to what's in the market as well. I'll show you that information in a minute. Bottom right, point number 4, these valves are sewn together into a frame, the bits of tissue of the competitor valves, and anywhere between 300 and 800 sutures are used, and it's done by hand. Now, those sutures act as a point of calcium binding, which is the first point. Secondly, they add significantly to the cost of goods and therefore the margin. DuraVar, because it's a 3D single-piece valve, does not need that many sutures, has about 20 or 30, which leads to a lower cost of goods, but more importantly, much less binding sites for the calcium. Now, if you could address 1 or 2 of these points, you would have already a step in the right direction for a more durable valve in the market. We actually address all 4 of those where nobody else addresses any of them. So that's quite important to note. Next slide, please. One of the ways we test whether our valves wear and tear outside of the calcium environment is to put them on a machine called a cycle tester. This machine pushes fluid through the valve very quickly and accelerates the aging of the valve. Every company has these. We test our valves on them. And it allows us to move a valve much more quickly to an age point that we can measure the wear and tear. You can look at this one here. It's one of our valves, DuraVar at day 1. It's 400 million cycles, which is about 8 or 9 years. About 2 weekends ago, we ran some valves past about 500 million cycles, which is about 12 or 13 years of normal use. It's obviously accelerated. It takes about 7 or 8 months to get them to that point. Now, there is a magic number here. The FDA requires that your valves must last at least 200 million cycles in order to get approval. We've tested competitor valves. Many of them fail at about 150, by the way, so it's an interesting number. The bottom number there, you see those 2.27 centimeters squared. That relates to the opening orifice, the EOA. Really important number. That measures how far the valve opens. Now, as valves get older and deteriorate, that hole gets smaller, less blood flow until finally you have to replace the valve. The DuraVar valve, because it shows 0 wear and tear at 12 to 13 years, that EOA stays pretty much the same, which is really important in terms of the clinical benefits and outcomes. Next slide, please. Here's one you can see. I don't know if you can see that video there. That's a valve. I think it looks pretty slow there. It doesn't actually go like that, but that's a valve in a cycle tester. When you're a physician looking at that, you get very excited. That valve is showing how a single piece valve actually works. The graphic on the bottom left is not anatomically correct, but it gives you some idea that the anteris valve rolls rather than slaps. And that's why we think it wears out more slowly. The design is actually far better than the current valves in the market. Next slide, please. Of course, we've gone into humans, and what you see there in that graphic is the echo from patient number 1. That's a Giravar valve. It looks beautiful the way it's working there. Now, there are many more patients we need to get. We just had patient 3 leave the hospital yesterday, I found out, but this trial is happening in Europe. Now, what I did ask the hospital who's doing this study to do for me is to give me some numbers so I could compare to patients who were getting these valves in that hospital, and they were using commercial valves versus our patient number 1 who had a Giravar valve. And the 3 things you measure to be able to check the viability of a valve is the peak gradient, mean gradient, and the EOA, the opening area. As you can see there, the peak gradient for the average of 1,400 patients with commercial valves was about 23. Our patient number 1 was 11. Mean gradient was 11. Our patient was mean gradient of 5. That's almost normal. So that's pretty amazing number. The EOA typically for a commercial valve is 1.5 to 1.9. Bigger is better. Ours is 2.9. That's really very impressive. It gives much better blood flow. Our patient who left hospital yesterday came out with an EOA of 3. So this data keeps replicating itself as we move forward. Next slide, please. So we are building the world's most durable valve by marrying the tissue science adapt with this incredible single piece 3D design. Next slide, please. Next slide, please. Next slide, please. 2020, obviously everyone's struggling with COVID and the impact on their business. We have had a fairly minimal impact. The biggest concern I had was doing the first in human study, obviously in a hospital, because hospitals were very constrained. Fortunately, we were able to get that study started, which was really important. Later in the year, we'll be doing a TAVR preclinical study with Giravar. We've started an anti-calcification study against one of the market-leading brands to show our superiority. And as a structural heart company, we're actually working on another project with ADAPT. It's a platform technology for the use in coronary artery bypass grafting, or CABG for short. There are no viable alternatives for CABG procedures right now. They strip a saphenous vein out of your leg. Apparently, it's quite painful, and they use that to bypass the coronary arteries that are obstructed. The ADAPT technology works very well. We are right now adapting some conduits, and we will be starting an animal study later in the year to test this product in the area of coronary artery bypass graft. There are about 500 million procedures per year in the States, so that's quite a big market as well. More on that to come. Next slide, please. We've got a lot of IP. We've submitted 18 applications this year. More to come by the end of the year. We probably will have done twice the number of IP submissions than what we did last year. Next slide, please. And we're really supported by a really great group of doctors in our advisory board. They've been with us for about a year and a half. We meet about every 3 months. These doctors are top of the tree in terms of TAVR in the world and come from some of the biggest centers in the States here. They're all very well published. They're all very well known. If I look at Dr. Kapadia there, he is the director at Cleveland Clinic. It's one of the biggest cardiac centers in the world. Professor Reardon, Mike Reardon there, was the principal investigator of the low risk study that led to that FDA approval I mentioned, as with Professor Popman from Boston. All of these doctors are very well known, very well published. They're on the podiums. They work with us and help design the valve and the catheter. So in the hands of these users, we have a captive audience once we come to market. I should also add, we're supported by a significant fund in the US who is headed up by a physician as well, who's originally a physician, and supports the company a lot. So the science is resonating. It's not only validated by all the research and studies we have, but it's also validated, of course, by the experts out in the field. Next slide, please. So I'll park it there. We are developing the world's most durable heart valve. I said it was a big claim at the beginning. Hopefully I've been able to very quickly validate that and tell you why it's important. But we've got the right science. The ADAPT technology is unique. Nobody has what we have, which is 10 years of data in humans showing zero calcification. We have the right design. Nobody has a 3D single piece valve in the market at the moment. Not only is it wearing out more slowly, much more slowly in fact, but it seems to have clinical benefits as the EOA is far better than what's in the market. So hopefully that'll keep repeating in the study. And it's the right time. The FDA have approved the use of TAVR in low-risk patients, which means younger. Therefore, the need for a much more durable valve is upon us right now, and the market wasn't quite prepared for that. I'll conclude my presentation there and go back to you, Tim.
Great, thank you for that, Wayne. A couple of questions. In regards to a product like this, how do you distribute it to the market?
So we will come to market with a partnership. We are in discussion with several of the big companies here. They're all based in Minneapolis, actually. The global headquarters for the big device companies are here in Minnesota, which is helpful. So, you know, typically you get from where we are in the clinical stage, we'll be submitting to the FDA for our EFS study next year, 2021, also to the Europeans. That's the beginning of the process to get registration. And we would go to market on a commercial basis with a couple of the companies who are already in the space right now, who are looking for their next generation TAVR devices to make sure they can maintain market share.
And so what's the like the business model here, the addressable market, the margin? How do you make a dollar?
We make a lot of them. The average selling price of one of these devices is $35,000 US dollars. And the cost of goods is probably confidential, so I'll leave that there. There's very good margins on these. There are only two real players in the market, and as I showed earlier, it's growing at about 16% compounded, up to about $8 billion by 2025, and it'll go beyond that. And that's without China in the mix, who are just coming online with these products. So really with two market players, there's, you know, roughly split 50-50. The chances that a product like DurAVR will get into the market is very high. We've got the support of those doctors. We've got the support of the big companies as well. So we would go in there on a licensing royalties kind of deal once we get through the registration process.
Okay, great. Wayne, thank you for your time. And we'll leave the US now and head to Canada. Next up.